Hi, in this lecture I will be focusing on transformations, why we need transformation, what is its importance, and for what kind of signals we have what kind of transformations will be cleared after this lecture. In order to understand transformation, look at this relation which is z is equal to 1 over x. If we put x equal to 0, then z will approach to infinity. 0 can be drawn on any coordinate system, while z approaching infinity cannot be drawn on any of the coordinate system. So uh, this is a kind of transformation equation which is transforming the z coordinate into x coordinate, because the z coordinate is an inaccessible point and cannot be dealt upon easily, but x is a kind of point coordinate system in which 0 uh, is the value which can be plotted in any coordinate system. So with the help of this transformation expression, z can be transformed into x coordinate, and in this way an inaccessible point of infinity can be transformed into accessible point. So this is the importance of transformation. Now what is its advantage? Its advantage is that when we transform z into x coordinate, then the solution of the problem in the x coordinate will come easily and on a faster track. If the problem was in z system, then it would require a lot of mathematical knowledge and a kind of a complex problem to solve in the z system, although it will be solved in that coordinate system as well, but by transforming it into the x coordinate system will result in its solution of the problem arrive at an earlier stage. So whenever we have a problem in the z system, we transform that into x system and do the solution of that problem on a faster rate, and when once the solution arrives, we inverse transform it back into the z system to get the answer. So this is a kind of advantage of any transformation, uh, by which we can transform any complex problem into an easier problem, get its solution, and then inverse transform back into the original coordinate system. We have an example in the logarithmic scale in which we have this kind of relation, in which we have a multiplied by b, and multiplication is a kind of complex operation, so we transform it into addition operation with the help of log values, and we solve our problem in the simpler, easier operator, and then once the solution arrives, we retransform back into the original form to get the answer. So this is an application of a kind of transformation. Now what are the uses of transformation in the signal processing? In signal processing, it is used in order to transform the time domain problems into frequency domain problems, and then getting their solution in the frequency domain, and then inverse transforming back into the time domain, because if we do not have done the transformation and we want to solve the problem in the time domain, then it will require a lot of mathematical knowledge and the problem will be in a very complicated stage and nearly impossible, and requires a lot of time to do the solving of the problem in the time domain. So that's why we are transforming into the frequency domain to get its solution and inverse transforming back into the time domain. So in order to get understanding of this situation, we have any human who is talking and his voice is mapped on a graph of the time domain in which we have x-axis the time and a represents the frequency, a represents the amplitude, and there is another graph which is also showing the voice of that human in which we have x-axis the frequency and y-axis same the amplitude. If we see that we want to do some kind of signal processing on this kind of signal, then this is a kind of continuous signal because the human is talking continuously and not in the form of robot by repeating words one after the other like that. So he is talking continuously and his signal is represented as a continuous time amplitude signal, while when we do its transformation in the frequency domain, we see that it is a kind of discrete environment in which we have representations of amplitudes of the frequencies at discrete intervals rather than as a continuous interval in time. And this is on the right hand side we have the finite number of frequency values, on the left hand side we have infinite number of time values. So let's see, if we want to do the signal processing of that time signal, then we need its mathematical function, and we know that the voice of the human is ranging from 20 hertz to 20 kilohertz, and if we have infinite number of points in the time, and we have many amount of frequencies which is coming in the human voice from 20 hertz to 20 kilohertz, and for one frequency we can represent that voice signal in the mathematical form by this function of t, where we can simplify it like where we have a representing the amplitude of the voice and cos theta is dictating the shape of that signal of voice, where we have the frequencies coming over here. So this is for any of the one frequency of that kind of signal, this kind of mathematical model is represented. But if we want to represent this whole signal, then we need a very big mathematical model which is containing a large number of this expression, because this expression is just for one frequency and there are a wide number of frequencies which are coming in that voice. So we have to represent this into infinite or many amount of these expressions, many number of these expressions, and then we have to, once we translate that signal into the mathematical model, then we can do the processing of that signal. But it is a cumbersome process and it is very much hectic and very much difficult and very much complex, and too much amount of mathematical knowledge is needed to do the kind of processing needed on the mathematical model of that signal. So if we come on the other side of the graph in which we have the frequency values which are finite number of frequency values, then we can represent our mathematical model with this finite number of frequency expressions, and it is possible, it is easier than on the left hand side where we have infinite number of frequency expressions. So if we want to do the same kind of signal processing on this kind of signal, then it is easier than that, because in this we have finite number of frequencies, and for those finite number of frequencies we can represent such kind of expression, and on that expression of that mathematical model of this demonstration, we can apply any kind of signal processing on that and get our solution at a faster rate. So that is an application of the in the signal processing, the transformation application, and in that application we transform any kind of signal from the complex, from not you can say a complex, these are both real terms, the time as well as the frequency both are real terms. So in signal processing we can transform our problem from time domain to frequency domain and getting its solution on a faster rate, and then inverse transforming back into the original time domain. So we can see our time domain signal on the CRO oscilloscope, and we can see its frequency representation on the spectrum analyzer, and we have in the spectrum analyzer the theory of the mathematical transformations of Fourier transformation is embedded in that spectrum analyzer, because Fourier transformations are the mathematical expressions which are providing a way by which any time domain signal can be transformed into the frequency domain signal. Now we will see a bit about the transformations. What are the transformations which can be used in signal processing? In signal processing, we have two kinds of signals. One is the continuous and other is the discrete signal. For the continuous signal, we have these transformations. One is the Fourier series, which is used for the transformation of continuous and periodic signal from the time domain to the frequency domain in the discrete and aperiodic form. This is the oscilloscope representation. This is the spectrum analyzer representation. And the Fourier transformation is also used for the continuous and aperiodic signal, while the Fourier series for the continuous and periodic signal. So the Fourier transformation is used to transform this kind of signal into a continuous aperiodic frequency domain signal. So these are the two transformations which are for the continuous time signal. And for the discrete time signal, we have any signal which is discrete and periodic and needed to transform it into the frequency of discrete and periodic, we need for that the discrete Fourier transformation. And for the discrete time Fourier transformation, in that we have input signal which is discrete and aperiodic, and we can do its transformation into the continuous and periodic form. So DFT is used for the practical purposes and DTFT is just for the theoretical purposes, and DFT is a discrete version of the DFT as well. And we have also the fast Fourier transformation, which is a fast version of the DFT, and it is providing a way by which we can do the calculation of the frequency domain components on a faster rate at a faster scale by reducing the complexity of the DFT algorithm. Okay, so we can have a brief introduction of about Fourier transformations over here. And this is an expression which is containing a continuous time signal and transforming it into a continuous frequency signal. So it is a continuous time Fourier transformation. And then we have a discrete time Fourier transformation, in which the integral of the continuous time Fourier transformation is replaced by the summation of for the discrete Fourier transformation, where we have an xn, which is any discrete signal, and t is the repeating interval of any sample coming one after the other. And if we want to take the uh, calculation of infinite number of points, as in this case we have time which has infinite number of time points, then we need integral. And if we have finite number of points like xn and discrete coming the samples coming at a discrete interval and repeating at with capital T, then we can use the summation operator for the calculation of the Fourier transformations. So this formula is for the calculation of the continuous time Fourier transformation for a continuous signal, and this is the formula for the discrete time Fourier transformation for the calculation of the uh, representation frequency representation for a discrete signal. And it is also coming in the continuous frequency transformation. It is transforming a discrete signal into a continuous frequency signal. So if we replace capital T by 1, uh, we can further simplify the relation of this discrete time Fourier transformation. And this is a relation for a inverse discrete time Fourier transformation, in which we have integral, which is representing the frequency limits, and we have the frequency continuous frequency signal coming over here, and 1 by 2 pi, and we are retransforming back into the original discrete time signal model, because in that we have W, which is continuous frequency indication, and the output is also containing W, which means that a discrete time signal is converted into a continuous frequency signal. So if we want discrete frequency signals, then we have to further discretize this W, and we have an expression over here which indicates equivalence of W is equal to 2 pi k over capital N. And if we replace that expression in the equation 5.6, we will have this kind of expression, which is indicating the transformation of xn into xk, which is k is indicating any discrete representation of frequency. So a discrete time signal is converted into a discrete frequency signal, and this makes it discrete Fourier transformation. And this is used in practical applications in systems because this xk is containing finite number of frequency components when compared to this xw, which is containing infinite number of components. Now we can see Laplace transformation in which we have complex frequency representation in the DTFT and in the CTFT and DFT. If we see this expression, this is a real time variable. It is a real variable, real frequency variable, and this is this is the complex frequency variable, and it is containing delta plus jw, where delta represents the real component and w represents the frequency component. So this is the formula for the Laplace transformation, which is doing the same thing as the continuous time Fourier transformation by transforming the real time continuous time signal into the frequency signal, which is a continuous time and real variable signal. But in the Laplace transformation, this variable is converted into a complex frequency representation, which is indicated by xs. So if we replace s with jw, then it is equal to the same expression of the Fourier transformation, which is the continuous time Fourier transformation as represented in equation 5.4. So this was for the continuous case, that if we want to transform any signal from time domain into a complex frequency domain, then it will be Laplace transformation. The person will be using that to do that kind of calculation. So if we further see, for the discrete case, we know that DTFT is can be calculated by this expression, and if we replace EST in that expression with Z, then the overall kind of expression will become this, and it is Z which is the complex representation. So if we want to transform any discrete time signal into a complex frequency representation, then we will be definitely using the Z transformation over here, and from that Z transformation we can also retrieve the discrete time Fourier transformation by replacing Z is equal to EJW. Thank you very much.